Hello and welcome to our talk, Bridging Safety and Architecture. My name is Tobias, and you already recognize, actually it should be two of us, Simon, whom many of you probably might know much better than me, but Simon, as you then also know, had some health issues recently, so he's still recovering. I spoke with him last night. We were polishing off the final slides for this talk, so he is very well aware of the content we're going to present, and I'm hoping that I'm not fully embarrassing him with what's to come. There's a bit of stuff to cover. I might need to skip one slide or two just to make sure we get some time in the end for Q&A, and I also want to highlight that right after this talk, and I think in the very same room, we have the BOF on safety. That's in the other room. Thank you, Nicole. So just then stay with us. 12:30 for questions, and then we can cover more discussions there. So that's Simon. You probably know Simon very well. He used to serve as a safety architect and safety chair until earlier this year, and then two new guys stepped up because Simon couldn't do it this year for the safety chair. That's Stefan. He's also in the room, and he will be then leading the safety BOF, and it's me. Tobias as my name, and I'm right now serving the role of the safety architect of the project. I've been involved with Zephyr mainly downstream, still to date, pretty much early on since 2016. I did the very first larger Zephyr project with a client of mine in the medical space in 2020, where it really helped us sailing the difficulties of the supply chain back then, and hopping from one hardware platform to the other, and making sure that the biologists we were working with back in the day could develop their COVID assay in time. And then we really hit a big bummer, which was regulation. And although the Zephyr-based R&D rigs were working just fine, the client eventually decided to ditch all of that in order to switch to a commercial RTOS again, which had certification. And that is why I actually stepped up, or why I became involved in safety and in Zephyr, and making sure that eventually we will have also Zephyr in medical devices and in many other devices that require safety regulations. So that's my personal motivation why I'm all doing this. Right now I'm with a company called inovex, and we are serving clients as consultants, as trainers. I'm doing lots of Zephyr trainings, so if that's something you're interested in, also come and find me. But for today, I really want to talk about a bit of the history and where we are with our efforts in getting a safety certification on Zephyr. Because I'm not sure about the audience, maybe some words for the introduction of where we are. So I just stole some pictures. I stole some pictures from the webpage, from our product gallery. So we've seen a tremendous rise and a tremendous increase of products really being developed with Zephyr in the last couple of years, probably in the last 2 years. But then there is a wide range of other applications where Zephyr isn't just quite there yet, and that's basically everything that is required with safety, which actually might already start with a washing machine. There is already regulation around a washing machine, but then obviously it's about automotive and industrial automation, robots, factory floors, and in my case also medical. So for those products, users have good reasons why they should and would like to use Zephyr. It's just that they can't right now without tremendous additional effort on their end. So what is basically one of the goals from the get-go of the project, and Kate mentioned that also yesterday in her talk, was safety and security. And we are just, need to work on that. So what is that functional safety thing all about? I won't go into too much details on the very basics. Suffice it to say that for functional safety, a good working software is not enough. Let's just leave it like there. So it's great, and we have good reasons to use Zephyr because we love it for the features it does and for the configurability and everything, and it is mainly working correctly, not everywhere. We've heard also some stories from others, but it's assumed functionally correct. But then there is more that we need to do to achieve functional safety. For instance, we need to extend, if I want to use it in a critical product, by means of active safety. That is, the system must on its own have measures to detect hazards or even to protect users from potential hazards. So there have to be additional mechanisms which might not necessarily be related to the actual product function, just to make sure that the product works safely. And another important thing is that eventually a product maker needs to go to a so-called notified body and has to convince the notified body, TÜV you might have heard, or others there are, that the thing is indeed safe. And that's what we call reasoning. So you have to be able to reason about the system. And that is, you need to talk to someone who is not a software developer. You need to find other ways of language and of communication that help you convey the argument, your safety case, that what you did is actually correct and behaves in a safe manner. So to take one quote, functional safety is the absence of unreasonable risk from hazards caused by system malfunctions, just to get it that one. Or the other way is we need to ask not only does it work, but what happens when things go wrong. So is it also safe when in some dysfunction. And then for this, the standard actually makes a distinction. Most of them do. I've just quoted the most important ones. The one that the project choose for good reasons, which I'll explain in a minute. This is the IEC 61508. That's a functional safety standard. And then for the automotive folks, there is ISO 26262, which is basically a paraphrasation of 61508, but I'm not going into details. Nicole is here, she is the expert on these texts. Basically, what I want to say here is there are two broad categories of failures that these standards look at. The one is completely absent typically from our software-centered world, and that is random hardware failures. Machines can break. A connector, a wire can get loose in the field, and then the software connects contact or to the pressure sensor that was monitoring the boiling cauldron or whatever. Or there might be the usual example. There might be some radiation event, cosmic rays, for instance, and you just might have a bit flip, or the hardware is in any other way affected. So there is a fault. And then these kind of things, although they are random, they are probabilistic in nature, you can actually address with architecture. One of the most often used architectural patterns you'll see is redundancy, and that's also shown here. So if one of the controllers is failing, you still have another one, and they're working in lockstep, and then you at least are able to detect the problem, and you can reach a safe state. The other thing that the standard also acknowledges is that you should and have to apply proper methodological processes. You need to design your software in a systematic way, and you need to make sure that you think not only about your product features, but also to a certain extent about all the things that could go wrong. That is basically the realm of so-called systematic failures. And in order to minimize those, as I said, you need to apply rigorous methodological processes that these standards mandate for you. And I'm just picking up a few here already because we come back to them on later slides. That's one is traceability. They talk about coding standards, and they talk about a whole bunch of verification activities that you need to go through as a product maker. And all of that, the standard then summarizes, and you will hear that a lot in the discussions, and then probably also later in the BOF, that's what they call a systematic capability. Now, why did the project choose 61508? Because in a certain way you can say this is the mother or the father or whatever of all these other standards that also address functional safety. So the field is quite diverse. For me, in medical, for instance, the standards are actually 6061 and 62304. They do not directly relate to 61508, but you will see a lot of commonalities. And the same holds true for many of these other industries, which I'm not so much affiliated with, like energy, household, industrial. So the idea, and I think this is a very sensible approach for something like an operating system, is if you go back to the main standard, although you have to do it downstream, but the mapping should somehow be straightforward. So that's why the project is not focusing on any of those particular standards, but is trying to solve that thing in the middle and then leave it as an exercise or as a homework to the product maker to do the appropriate mapping to whatever standard they are using. Just one slide, I thought about putting a bit more in here, and I've been also asked that in communications. What about security? And I like the English language a little bit better than the German one on this one, because it's more precise. So security, as you all know, and we mean cybersecurity, is to protect machines from maliciously acting humans. So we want to make sure that the machines cannot be misused, information cannot be stolen, whereas safety is protecting us humans from machines when they go wild, like a robot arm that is moving and like kinetic energy that could cause harm. These two things have been at odds in the past, I'll come to that, but nowadays I'd also say, and I'd like to argue like that an insecure system that is connected is by very nature also unsafe. So I would consider security a prerequisite for safety, because if you can compromise a system, you can undermine all the safety measures that the system has, or most of them if they've been implemented in software. So you cannot make an insecure product safe. That's not to say that any secure product is also safe in automation, right? I mean, it can still be unsafe, but security is important also for safety. Why has there been at odds in the past and there is still a tension? That's because safety products were kind of one-offs. Once they were working, you wouldn't touch them again. You just do not touch that. It's working, and you have proven that it's working. With security, things are a little bit different, as you know. One of the biggest ones with security is to get updates out in a timely fashion. We learned about the notification dates, and then the question becomes, if you have a security update and you get a window from the administration of 30 days, is that enough to go through your safety procedures again, to really make sure that the safety standards and the safety claims you were making about your product still apply? So there is a bit of a tension, but maybe that's for the BOF. I wanted to mention that. Now, the other big one in the title was architecture. So what do we mean by software architecture? Now, as I said, I've been in the field, I've been doing software architectures and system architectures for medical devices last 15 years. And I'd like to look at it as the macroscopic structure, the broadest thing, the conceptual glue, you might say, of the software system. It's not about the nitty-gritty details, it's about all the significant design decisions, like how is the software organized, what are the constituent components, the interactions, externally visible properties. The main tools that the architects have are abstraction, decomposition, and composition. So you break the system, you break it into smaller, more manageable pieces, and then you define the rules of interaction by which these systems do interact. And that gives you the ability to reason about the system by these means of abstraction. You do not need to know every single C file to the minute detail. You talk about abstractions. Architecture is also a process. It's an activity that you do, and the standard mandates that you do that as an explicit activity. And that means in doing it as an activity, I need to consider so-called quality goals, for which, for instance, one might be safety, maybe then the most important one, where I need to make trade-offs. A typical trade-off decision in architecture is between performance and safety, or between resource usage and safety. We had the issue, I think it was roughly Christmas last year, when there were some benchmarks being run on Zephyr, some of you might recall. And then, they came out a bit bad. And then the reason was that on default, we had hardware stack protection turned on, and these benchmarks were running with hardware protection on, and that had a penalty hit, like a performance hit. But that is one of those trade-offs. Obviously, if you have it on, the product is able to detect stack overflows. So that's also something that architects need to do, and they also need to communicate and reason about the software systems. For instance, to an auditor, like what the project's doing, we need to explain, like to the auditors from TÜV, that what we've been doing is safe, and that is also one of the jobs in architecture work. Now, every software system has an architecture; you cannot avoid it. The question is, how explicitly have you documented the architecture? How much is really known and is extractable without staring at the source code? Obviously you can, and that's my day job, reconstructing architectures from big piles of code that customers throw at me and trying to like sense making. What have they been thinking when they did that like 10 years ago? I mean, I can earn money with that, but it would be much simpler if actually the architecture would have been written in the first place. And I'd say in Zephyr we cover quite well the middle grounds, so it's not just like that big ball of something, and we'll come to that. Okay, after this introduction, let's take a bit of a closer look into this and how that all relates to one another. So like, how does functional safety relate to architecture? Now, in functional safety, we start with hazards. That's something that, if it would go wrong, could harm people or could harm the environment. And from those hazards, we or the product maker needs to derive safety requirements. What does the system, the product, need to do in order to prevent that hazard to happen? And then what you then do is you need to implement this, and this is where architecture kicks in. If you just go right to the big ball of code, you will probably find yourself in a situation where you cannot really reason about and argue that actually this is going to work, and under all circumstances, that you have covered the grounds thoroughly enough. And with a proper architecture where you can follow a certain way, if this happens, then this happens, without going through every single line of code every single time, that gives you the idea that you can actually argue in favor of your safety case. This is this reasoning thing, and that's been, as I said, mandated by the standards. It's 61508, it's the section 7 in -3, measures and techniques to provide safety properties. You can read it yourself, and also an appropriate notation and verification activities. That's also important, so we need to find a way to document what we're doing that is recognizable by people who have looked at this from other vendors. So we need to bring it into shape for the auditors as well. They become stakeholders of our documentation. And last but not least, and that's been something we've been looking into much detail, is traceability. You need to be able to trace everything from those safety requirements to the architecture, to the design, to your testing activities, so that there is a full chain of audit trail. Closer look to architecture, because that is also probably a slightly misused word, and I mentioned that actually for me it's more to the left of this slide, where that's really architecture, but then and I would say the right side is more, I would call software design. This is still not writing code, by the way. This is still thinking about what eventually would become a C file or something. But then others tend to talk about distinctions like subsystem architecture, modular architecture, detailed design. The bottom line of all of this is, I would agree, and I would basically argue in favor that this is a continuum of things, and it's not so much a point of saying, oh no, this is not architecture, this is design, or vice versa. It falls on that spectrum, but the general directions is, the more abstract it becomes, the more it is architecture, and the more it is probably also in place since a very, very long time. So maybe some of those architectural decisions are no longer recognized as being decisions because they were made like 8 years ago. Most of us were not involved when these decisions were made because we joined the project later. Nonetheless, they are decisions, and things could have been decided otherwise, so we need to write them down. We need to write down that these are the decisions that were made, because they have an impact also on what we need to do for the safety. Obviously, innovation is not driven by long-standing carved in stone things, so they go more to the detailed design, and we'll see that come up later again. Give you some examples just to make it a bit more tangible. Picking up two often heard hazards. They have to do with a so-called freedom of interference. You can basically distinguish between temporal interference and spatial interference, like I do not want to have a low priority communication task clocking up the CPU, preventing a high critical monitor temperature monitoring task to run, and that would be called temporal interference. Or I also do not want to make sure that if something goes wrong in a low critical UI task, memory of my critical task gets overwritten. Like I want to have this spatial interference freedom that one task cannot corrupt the memory of the other. There's actually, now you see the hazards, we can re-articulate these hazards in so-called safety requirements, and from them I can now derive architectural design. And for us and for these examples, we might actually say, okay, to avoid temporal interference, we're going to need a preemptive priority-based task scheduler. And you can read it yourself, for the spatial interference, we can also come up with some architectural solution. And what you also see is that is actually, although it will come up in a product, this is not really product specific. These are actually responsibilities and architecture patterns of an RTOS. So that's why obviously I choose those two. There are probably also lots of safety requirements which will always depend on the actual context of your product. But these are not so. And this brings me to us as an RTOS project and what we do in order to compile what we consider our safety requirements. The Zephyr project, on its own, has no prior safety context. We are not making a product. The project is concerned with providing a set of software functions of source code that is an operating system. So that's what Zephyr is doing. And I already put in parentheses, and I come to that again. I'm not now talking about the whole of Zephyr. I'm talking about what has been decided to be the safety scope. The project also has a lot of other stuff, there's modules, the SDK, and so forth. And then on the other side, we have the product maker. My medical clients, for instance, or the automotive industry, they want to use Zephyr in their product, and that's where the safety context comes in. So you need to understand the product in your safety context, and then Zephyr is integrated into this safety context and that's where the name comes from, a safety element out of context. Actually, the standard itself calls it a compliant item. And here you also see some of the homework that we need to do. In order for these integrators to do that, the project needs to provide what's called a safety manual. And the safety manual needs to state, besides many other things, the ones I put on the slide, we need to say the assumptions under which we make the claims about the freedom of interference, for instance, spatial. If we, as a project, rely on the MPU, then a basic safety assumption that would go into the safety manual is, if you want to use it then in your product, you need to use a microcontroller that has an MPU, because otherwise we cannot guarantee that the measures we implemented will actually hold in your case. So that's the kind of documentation we need. And the standard is also very clear on that we need to provide the rules, and the integrator must adhere to the rules. So it's a double-sided contract to make sure that the thing remains safe. That's, for instance, also explicitly stated, made me smile a little bit. The standard talks about the competence of the integrator. So what competence level is required by the integrator? What do we think as a project the competences are that an integrator needs to have? Like being able to use Git, for instance. I don't know, we'll come to that. Another big one, and that's why I think the progress is not as fast as it could be probably, is there is a fundamental, at least that's and I can argue about that, but I see it as a fundamental impedance mismatch between the world of the standards and the world of the industry and what open source really is about. And that's because these safety standards are, in essence, process standards. And being process standards, they make a fundamental assumption, namely that these processes are being executed by a company, by a corporate, where you have a control structure. Someone can tell someone else what to do and what not to do. And this mandate we do not have as an open source project. We can obviously reject unsuitable work by means of the PRs, but we cannot mandate required work to happen because we are contribution driven. We are not requirements driven and by and large. So where we are bottom-up dynamic, the requirement that the functional safety actually wants top-down and favors stability over innovation. So that is the conundrum that we need to solve in one or the other way, actually the conundrum that every single other open source project also needs to solve. And we'll see that coming up again in the remaining of the talk. Now, what did we do in the Zephyr project? And as I said, I wasn't there from the beginning. I only stepped in like a year and a half ago. We had to, or the project had to establish these processes required by the standard. There had to be entities that could address these things, that could steer and drive these processes. We also have to backfill missing artifacts. There is no requirement specs, as you all know. It's in the works, but there wasn't a requirement specs to start from. The thing got released on GitHub in 2016, as is. And that is, for me, the biggest challenge, because that's where I've seen a lot of churn in other projects being produced in the last years, is we need to find a way to keep in sync with what happens upstream. Just for the security mandate alone, it doesn't matter if we are ready. If we declare completion in 2027, we have 4.7 or 4.3 now safety certified, and then everyone says, hey, but we're at Zephyr 7, so what is that about? So that's the other challenge we have, and we need to do that in a FOSS-compatible way, otherwise we will not get acceptance from the community, of course. So what has happened? I put it down into 4 steps. 2 of them have been completed. The project has founded a safety committee, which comprises the platinum members. There is now also a safety working group, which is open to everyone to engage in discussion, to come and chat with us, to help us. There's also dedicated budget by the safety committee, because the TUV is not free willingly look at the stuff. They typically ask for 1 or 2 pennies. There is the role of the safety chair and the safety architect. So these were the organizational structures that had to be put in place. There was also a discussion that has settled to some extent, although it's not, well, obviously this is not never ever final, but we have something to work with, that is the safety scope. And now what is ongoing is we need to still define or flesh out or refine, I'd say, the working model. Like, how do we now work with each other? How do we collaborate? Who is actually going to write the requirements? Who is actually going to do the verification activities and so forth? How do we integrate all of that with the rest of what happens in the project? And then this is the compiling the evidence, the paperwork that actually needs to be submitted to the TUV for certification. Scope matters because there is a lot of documents that need to be written, as probably all of you know who have been in these industries, because the basic rule of all these standards is if you didn't write it down, it just didn't happen. So you have to have these documents, and our documentation, for good reasons, is aligned with what we need as a FOSS project. Not necessarily, I think the micro broke, anyway, not necessarily in these papers and the documents with the titles that the standards expects. We got our documentation, we have issues, PRs, where a lot of discussion takes place. We got Discord, source code comments, it's all over the place, and for good reasons, but not necessarily in a way that we can actually ship that to the auditor. So getting this evidence is significant effort, and we need to make it sure that it's achievable, it's realizable. So what the project decided on, and I just refer you to this issue where that discussion took place, and is probably also still being taken place, but there is some initial scope which was decided, which is the kernel services, system initialization. So basically, others have called it just kernel-star is the safety scope. That's probably also fair to say, although there are some exceptions to that. The point is, we are down from nearly 2 million lines of code to roughly 15,000 lines of code, if you consider that. So it's a significant smaller portion of what we're talking about. And for this, it is still a lot of work needs to be done, because we need all these documents that are now shown, because that's what comes from the standard. We need to have these safety requirements. We need to distinguish between architecture and design, because that's the expectation. That doesn't need to be separate documents though, but what has been your architectural decisions versus what were your detailed design things. We also need to do study code reports, verification reports, integration tests, all of that stuff, and including the traceability. So just to get that up for these 15,000 lines of code is already a challenge. Coming back to what does that now mean for us? You've seen that before. This is the spectrum, and this is not a full list of design decisions, but just to give you some examples of what decisions I have in mind that also have implications. Like the project a long time ago decided, for good reasons, that our implementation language is C or C99. That was an architectural decision because it affects the whole code base right now. And if we were to say, oh no, let's drop C, let's do Rust, that might mean a rewrite of everything. So that's why it is one of those high impact decisions early on. We also early on decided on Kconfig for feature management. That's been in there from the get-go, at least what was publicly available. We have the CMake build system. We have code generators written in Python. I come to that. This is something which is not as hard because that can be changed. It came also later. We have our linker sections. That's also important. Memory protection. And then also, obviously, while this is true for everything in Zephyr, we have some more specific design details which now also go into the safety scope, which is the kernel API design, say. So that's more changeable, and I know there's been discussions about renaming functions and stuff, but that's not the fundamental architecture. That's more detailed design, but that's the kind of things that we need to grasp, that we need to hold on. Again, just what does that look like and what we need to do? I'm not giving two examples again, just the one on spatial interference, just to give you an idea of what I'm trying to convey here. We had this issue with the spatial interference, and we might have these architectural solutions. We're going to use hardware-assisted memory partitioning and exception handling. We'll have Kconfig for software feature management that you can turn that on or off. We have you use the CMake build system because certain scripts need to run in order to prepare the syscall APIs. And obviously, we have a design pattern that there are system call semantics in tree. That's all decisions that were made at the architectural level. And then how do they realize? Obviously, we have Kconfig features, we've got linker scripts, linking stages, we have an implication onto the source code, and we have lots of tooling. So these are the things now that we need to look into and that we need to verify that they actually work the way we think or we claim they to work. And then for the safety manual, we need to have our assumptions in place. Like if you want to use user space, Arch has user space, needs to come back true. We need to tell the integrators, oh, and by the way, if that is the way you want to reach your interference freedom, you have to turn it on, maybe even both of them. So that is what you need to put into your project conf. And then there is also a guideline, probably, that we need to tell them, and you have to make sure your tasks are user mode threads. And if you have something in the main, that also drops its privileges to user mode. So that's kind of the content you would expect from these different documents. How much time, actually?
7 minutes left.
Oh, that's way than enough. Okay. All right. So where have we been? What has been the journey so far? We had a lot of discussions also in the working group, and that's really one of the points that Simon wanted to bring home, is that we as a project, we're not a company, we're not an organization, and some of the discussions were centered around that people were bringing their corporate standards to the discussions, and oh, this is how we do it, and this is how we do it, but that is not necessarily how we as a project can do it. So we need to go back to the very standard itself. We do not, that was one of the lessons, we do not need, we need to read the 61508 ourselves and come up with something which matches the project. That's been a slow process, but it's important, and it's also important to understand for people joining us that there is a reason why we are doing things slightly different to what you are used to in your company, because we aren't. So that's one of the lessons. And one of the examples that, and Simon was very much involved in this, was the coding guidelines that we made the decision. Now we can see the trace. We made the decision for the C programming language. The C programming language itself has ambiguities. To resolve the ambiguities, you need to apply a coding standard. You have to reduce your C to a subset of what you could actually do in C. That's been enforced by coding guidelines. They are mandated by the standard, but not necessarily MISRA. MISRA is one of many standards. But it doesn't say anywhere in this document it has to be MISRA. So what the project said, because we have to have something, is to go with a subset of MISRA. So not all the rules in MISRA are in our coding guidelines. So that's just one of the examples where we need to find our own way. So because we had that discussion, no, this isn't MISRA and this isn't MISRA. Is it compliant with our coding guidelines is the question we need to ask. What has been achieved, and again, that is that would have been Simon's part for sure, because he put a lot of effort into this together with Nicole last year. So we have coding guidelines in place. I've provided a link to them, but you've seen them in the documentation page. We have integration for static code analyzers in the build system, SCA systems, Eclair, and I've forgotten the other one from MathWorks, but at least two, and CPP check is also there, and we've seen support by the companies to also map or implement our coding guidelines into the tool-specific setup. So if that's something, there's also the guys here in the conference, if that's something you're interested in. We have a repository, which right now is not in tree, for the requirements. You can check that out yourself. We have made a start, but then I also have to admit it's been slow. We're lacking hands and heads, start to finish, to help us shaping that out. We also have a strategy, which is on the documentation of what we want to do in terms of requirements, which is very close to the kernel API. And that was probably the biggest milestone achieved by end of last year. There were discussions with TÜV, and there was a concept report prepared, and the project got confirmation from TÜV that, yep, what you've put down there as what you plan to do looks like that this is going to achieve the goals that you've set out. So that was a big one. So the plan's looking good. It just now needs execution. So if you know, anyways. So. And the other thing is, the key to the sex is we're going to need to involve the community. There is a lot of work to do, and it has to be together with the community. That's where we are. Now, on the final minutes, I'd just like to take a slight look ahead of where we are and what I also envision like as the future of open source and functional safety, because these worlds right now, they feel like light years apart, but they are getting closer, and it's not only in the Zephyr project, it's elsewhere, and the reason is simply because open source is eating the world, because we all want to focus on the value differentiating features. So the commoditization of software stacks, eventually this race to zero is ending up in open source all the way, and functional safety is no exception. But there are these impedance mismatches. So the good news is it's not only Zephyr doing this. There are other examples, most notably the Xen project is trying something very similar. ELISA is also looking at Linux as a safety element out of context, at least so is what I learned from Nicole. And there's a cool talk later in the afternoon, 4:20. If you want to hear about more safety element out of context in the case for Linux, Kate and Nicole are presenting another talk. There is the RTMS project, which has been in space. It has been ESA funded, whereas there are some precursors, other RTOSs as well. So it's not only our mission to do that. Unfortunately, I mentioned the the challenges already, and one of them is obviously that we are an open source project. We are used to the fact that what we're working on is freely available. These standards are not. You have to typically pay some money to get them, and that also makes it hard to get buy-in from people to contributing to this if there is this paywall, basically. I found this webpage quite helpful because it's all legal. It's not like Pirate Bay for standards, by no means, but they are affordable at this page. It's an Estonian website, so, and in the EU at least you can get some of the standards from them. Same true for the MISRA coding guidelines. The MISRA standard itself is not free, but it's no longer a problem for us, as I said, because we have got our own coding guidelines now. And then obviously the reality also is that because there is so much more that you now need to look at, not everyone in a FOSS project might actually care, right? It's functional safety is not for all of us. So we need to find a balance between the different interests. Zephyr is evolving. I mentioned that before. We see like 6,000 commits per release. That's actually pretty stable now if you do the analysis. It comes roughly always like last 3-4 releases at this speed, which is tremendous, right? This is like 40,000 commits from one LTS to the next LTS. This is how fast the whole thing is evolving. Obviously, on the safety scope itself, it's not that much, but it's still considerable. It's still like 60 commits on average between 2 releases on the kernel repository. So that is what we would need to look at more carefully if eventually someday we might end up at having these things on main. We're not there yet by no means, but it might be desirable because then it also means that we can also follow security more easily. The ideal situation, as you know, is, or as I just said, we can get the safety documentation in sync with main because it's considerable effort to create this documentation in the first place, and it falls out of date the moment we write it. No one's really won anything. We need to find a way that security updates that are necessary. That's my view now. That they won't interfere with our safety claims, so that we can also roll them out to the field. And then recertification of major releases eventually one day become no-brainers. And we do not need to go through this process that we are now in over and over again. And we need to find a way to get that done with the community so that we are not putting too much burden on the entire community. But where is the fine line? Where is the trade-off? I think that's something that needs to be discussed. For this, I have also to say we would be first movers, boldly go into the unknown, because other projects have decided on different strategies with forking, basically freezing, and then doing this on this freeze, but then what? So doing it in that way is more challenging. That's why we do not know exactly how it works. But eventually, it's also obviously more rewarding. And that brings me to the conclusions. Back to architecture. I like to think about what we're doing in terms of actually 3 architectures that we've touched on today. Obviously, the software architecture of the product itself, or the Zephyr RTOS in our case. There's also this information architecture that we need to map. Where is what piece of information written? How does it trace to? How is that all organized? And then we as an organization, as a project, also have to have the means, the architecture to support all of that. And these things are mutually interdependent. And we cannot look at one of those in isolation from the other. They relate to one another. And that's the pretty much very last slide of what I went through with you. Functional safety requires architecture as per the standard and for good reason. We need our documentation to be fit for purpose, not only for us as developers, but also for these other stakeholders. We are on our way. It's slow. We need helping hands, so please feel free and join us. And we'll keep you updated on events like this or on the working group for the foreseeable future. So thank you very much. questions, comments?
Speaking about the scope of the project in terms of like the internal associated rules, you mentioned about
Yeah.
say Unix libraries or schedulers internally. Well, speaking about scheduler, then immediately it jumps to context switch, and then immediately speak about architecture specific context switches. So how limited that scope would be in terms of the code base itself, scope of the safety itself?
As I said, the question was, thank you, the question was about, if I got it right, that when you talk about schedulers, you get hardware-specific code fairly soon. Because the context switch happens in an interrupt service routine. Well, yeah, I think this, whatever needs to be in place in order to serve the API, the kernel API, needs to be considered. And that's why this kernel dash star is more like a, what's the word, eyeballing of what we need to look at. It's not that all the files eventually will really, it's my current interpretation, reside underneath that, because we need some architecture-specific files from elsewhere.
Yeah, the scope is then like not limited to kernel by itself, but also covers the architecture portion, or it's not?
The hardware architecture, you mean?
Something like ARM
To-
or
It has to. We will not. The current plan is not to go for real hardware for testing, but to look at this in a virtualized environment. But even that means there is some hardware-specific code that needs to be included. But that will be looked at later, I guess. What specific architectures that will be, like ARM, Cortex, RISC-V, whatever. Yeah.
We're going currently for hardware agnostic, so we look into it for tests, but not for the certification scope.
Yeah, but even then, you need some hardware-specific, hardware architecture-specific code to make it work.
Yes,
That's the
but
point. It will not be in scope.
Yes.
Okay, thanks.
the main reason is like kernel by itself is tightly coupled with respect to architecture. It's not like you can completely pull the kernel out and test the test.
Right, but then what you still have as a degree of freedom is what is your test bed versus what is your subject under test. And then you might also be able to consider, we need to argue that with, it's not complete, but you might then argue, you need to provide this architectural code in order for the rest of the system to function. Yeah.
So yeah, you mentioned now that because of the safety element of the context, there's a subset of Zephyr
Yeah.
that can be used for safety. So is there already a guideline, even in draft, for vendors to implement their drivers that will be safe related, or for integrators to have their main thread in applications?
No, not to my knowledge, not at the moment. It's work in progress, basically, much, yeah. Yeah.
Yeah, maybe a follow-up question on this question. Suppose I want to bring a medical device on the market. How should we deal with this? Like the hardware abstraction layers, which are an inherent part of Zephyr, because all software provided, for instance, by NXP is then used
Mm-hmm.
to run Zephyr on top of that. You have your device drivers. What's your take on this? How should we deal with that? I understand that it is not really the scope of the thing that you're covering right now, but as a
Right.
product vendor, what is the take on this? What is your take on this?
So, just jumping back, and we can probably continue the discussion also on the BOF. So in medical, and thanks for the question because I feel more safe in medical than anywhere else. What Zephyr would be looked at basically is what's called software of unknown provenance, because you have developed that not according to your own process standards, and that would also be true for any vendor HALs that you're bringing in, any other middleware that you're bringing in, and you need to qualify this. And the idea is that if you get something which has a clear defined interface and for which some of these documents already exist, you can lower the burden on your validation process significantly, but that is not to say it goes to zero. So you still have to do the risk assessment, you still need to document your risk mitigation measures and all of that. But Zephyr is like with the other commercial ARTOSs, it's the same discussion, and I think they're overselling on that point significantly at trade shows and elsewhere, where they try to get you into this mood of, oh, you can forget about everything, it's all certified. Well, by no means it is. It is the kernel that got certified with safety assumptions that they made on behalf of you. You still need to check all of that yourself again. But for the kernel, you do not need to go through the architecture of the scheduler and the semaphore. That's been carried, or that's been taken care of for you. Yeah.
So a question for the future, can we create this and when this is done for the medical space? I know there are like several different levels of the
Yeah.
of the devices that you can make.
Yeah.
So could these ever used as modules for those really high-level devices that I'm talking about, pacemakers or
Right.
something like this? Would application developers still have to do extra work, or would they use it, or they can pick it and they didn't use that because it's open source and it's not
Yeah. Yeah, thanks for the question. The question was about what is the level of criticality that you can eventually address with Zephyr in a medical device like a pacemaker. So the project right now is aiming for SIL3, safety integrity level 3, which is kind of ASIL-D, is that right? Roughly comparable.
minus a little bit.
So that's these standards. That does not directly map to medical. It's actually the 61508X interestingly makes the explicit statement that it is not meant for medical devices because it's been covered by 6061. But then 62304 makes references back to 61508 that the practices in there are actually also what you need for medical devices. Yeah, you can spend your entire holiday in these standards and and lose yourself. So in short, it will always depend on the risk profile, and you will always, as a manufacturer, need to make the final call on that. So I wouldn't rule it out, but then what does it really mean, SIL3, in the context of your medical devices? SIL3 is basically about probabilities, like the risk as harm times likelihood or something. And the higher these numbers, the more bad things could happen, or the more often bad things could happen. So that's, yeah. One more question maybe to take, and then.
I want to say the discrepancies between 61304 and 61508 is easy to explain. 61508 is saying you can't use it for the analysis for the system level of medical devices. You can't use 61508 for the software and hardware of medical devices. That's a discrepancy because in a lot of medical devices you are intensely inducing harm.
Right, very good point, yeah.
Harm you can't use.
Yeah.
10 to the minus 6 probability of
Yeah.
And the other thing with respect to medical system, class C is by definition excluded in the current system.
Yeah.
So you never consider each class C, which would be a pacemaker.
Okay, thanks for the clarification. Okay, thanks. I think we're well over time now. I think we should let go everyone, grab some lunch. Thank you again.